Everyone, thank you for coming. Our next talk is comparing approaches to structured concurrency. And some fun facts about our speakers. James is co-authoring a book about effect-oriented programming that utilizes Scala 3 and Zio. And one of Adam's biggest passions is biohacking and improving human performance. So please welcome James Ward and Adam Hearn.
Awesome. Well, thank you all for coming. So a little disclaimer. We just signed up to do this talk like a week ago, so I can't make any promises about the quality of the talk. Yeah, you can feel free to leave. What I can guarantee is that this guy actually knows what he's talking about. Not me, but he does. And so I did bring an expert with me that'll teach us all the things. So go ahead and introduce yourself, Adam.
I'm Adam. I work for Amazon. We build services with Zio, Scala, I think, and a lot of other things, of course. But I think structured concurrency is pretty cool. And I think you should probably use it. So that's my pitch.
That's it. Okay, and I'm James Ward. Just joined Amazon a month ago as a developer advocate, and so now I get to play with languages and help people learn about AWS. So let's dive into structured concurrency. So I want to start with just a little bit of an overview on what structured concurrency is and some elements to it that we'll be covering today. So the way that I think about it took me a little while, is like, why do we call it structured concurrency? That implies that there is some structure to it. And I think that generally the structure to structured concurrency is that it's hierarchical. So taking concurrency and applying some hierarchy to it. And this gives us some things that we can do that are generally pretty hard with normal concurrency. And so one of the big ones is cancellation. So when we define our concurrency in terms of a hierarchical structure, we've got a parent with children. Those children can have children. So creating like a node-based graph of how we've modeled our concurrency. And one of the cool things is that cancellation can happen across this graph. So if we cancel the parent, then the children will get canceled as well. And
I think we talked about this a lot, like tree pruning. I think we don't generally think about fibers, threads, whatever, as trees, but when you sort of visualize it like this, a parent may have many children, and if a parent dies, then obviously all the children should be pruned from this tree, and that could be non-trivial, because we'll get into later, but like resource handling can be, non-trivial. And so I think the important part about like pruning, let's say, is that if a leaf dies, it doesn't necessarily mean that the parent computation dies, which is maybe not so true with, let's say, classical concurrency. Yeah. I don't know how we want to phrase that. But.
Yeah. So one of the big uses for this is a race. And a race, we're going to get into this deeply today, but a race is just like saying, all right, we've got a parent. It's got likely 2 or more children. Races with less than 2 don't really make sense, but 2 or more children, and we're going to be able to race these 2 or more things, and then propagate the result from the winner of that race up to the parent. So we'll get more into that in a little bit, but typical place where we use that. So one of the challenging things with concurrency is often around resource management. How do we open and finalize resources in a safe and expected way? And so, what about resource management here with structured concurrency?
If you've ever written in Java and you've tried to use try finally and it doesn't work how you expect it to, it's probably not your fault. It's probably an issue with the abstraction. Okay, maybe it's your fault, but for today's talk, we'll call it not your fault. Yeah,
it's just hard.
Yeah, so I think with structured concurrency, we want our abstraction to have a first-class mechanism for handling resources, finalizing resources, and I think this is key to basically building scalable apps and not getting lost in the weeds at every point you need a resource.
Yep. Okay, and then I think a big part of this often is around resource management, how we can correctly and best use our resources. And so this is being able to use efficient thread utilization when we're doing structured concurrency. So having fibers, being able to manage how those fibers get executed on OS threads, and then being able to do non-blocking I/O as part of this. And we're going to be diving into examples of that. Anything to add to?
I don't think fibers are necessary for efficient thread utilization, but I would concur that you do need efficient thread utilization if you want to build any non-trivial app with structured concurrency.
Good point. Yep. Explicit timeouts are something that are often used in structured concurrency to be able to say, all right, I've got this child down here, I'm going to set a timeout on that, but then if I set a timeout on the parent, that should then propagate cancellation across to the children. So this ultimately is just a race. We're going to see this in a little bit, but it turns out timeouts can be modeled just as a race between something that takes time and then the timer. And so it becomes a pretty trivial thing to implement with structured concurrency and do all the cancellation and resource management, all that stuff well.
Cool.
Okay. And then semantic errors become another important piece that we'll see a lot of today, because with structured concurrency, we often want to know, did this task actually fail or did it succeed? Because we may want to have different semantics, like in the case of a race, we may want to have a race that only actually completes the race, where the winner of the race is only considered a winner, if it did not produce an error, if the thing that was being raced didn't produce an error. So,
in other words, we're focusing on the result of the computation, which is, I mean, generally what we want as programmers. We don't actually care how the computation works. We just want the value. And I think semantic errors give us an ability to abstract over this idea and say, losers in general, we want to treat them, just because it failed doesn't mean that it should ruin my rest of my, execution.
Yeah.
So.
Yep. Okay. So now on to the structure for how we're going to be comparing different languages and frameworks. I started working a while ago on something called Easy Racer. The concept of Easy Racer was, can I set up some obstacle courses around those different elements of structured concurrency that we just talked about and compare how different languages and frameworks meet those obstacles? And so there's a lot of different implementations of these. I've built some of them. Other contributors have contributed some. I don't know OCaml very well, so somebody contributed those. There's a bunch of Python ones. Most of them don't work because Python. And so you can check those out, or you could help me get them working, maybe if you know Python and want an adventure. And so, yeah, it's been a fun way to experiment with these different ideas of structured concurrency and how these actually look in different languages. So that's Easy Racer. It's all open source on GitHub. And the Easy Racer server, so the way that it works is there's a server for Easy Racer. That's actually built with Zio and GraalVM native image, and it comes in a Docker container and starts up like instantly because it's GraalVM'd and all that kind of stuff. So it's kind of a fun reference implementation of a Zio HTTP server with GraalVM. But you can just run the Docker container, and then you create the client, and the client is going to open requests to the server, and the server is going to try to do its best to validate that you have kind of met the obstacle, each of the 10 obstacles. So that's Easy Racer. Today we're going to be going through 5 different implementations of Easy Racer and the different scenarios, and we'll spend a bit more time on some of those than others. And all the code you can go through and see on your own. But yeah, let's talk about the 5 different implementations that we're going to be going through today.
So as many of us, I mean, if you've used Scala, then you're probably interested in effects. I think a lot of us are. If you've used Haskell, maybe there as well, or TypeScript, that's okay too. In general, I think we view all effects as monadic, but that's not necessarily true. So in the case of Scala Zio, it was sort of revolutionary in the fact that it enabled us to do many things with one monad type. We don't end up with this horrible F-bounded polymorphism, which maybe some of you still enjoy. But the problem with this is it's a very heavyweight abstraction. I think for many things it does well, but a recent or new contender in the space is Scala Kio, which is, let's say, an algebraic effect system with a single monad which can handle arbitrary sets of algebraic effects. So we'll get more into that. But then there's also these direct style. If you're on Twitter, you certainly know, or I should call it X, I'm sorry. You should know that direct style is very contentious right now, and for better or for worse. We're going to call it imperative programming because that's what it is. So if you've heard of Scala Ox, it's a Loom-based abstraction. It can only run on JDK 21+, but the benefits of it is that it's efficient resource utilization. So when you do these structured concurrency things, you don't need to be using effects. All of your functions have pure value return types, which is certainly a benefit. We'll also talk about Rust, which is, of course, a future-based syntax with some sugar over it, right? So when you call await, async await, whatever these functions are, they're really just features under the hood. And we can get more into why Rust features are awesome and why they suck, but that's for later. We're also going to talk about scope-driven development. This is something that's unique. I would say maybe not unique, but certainly similar to Python's implementation of like nurseries. I don't know if you guys have heard about that, but this will be solely based on Java Loom and using just Java code.
Yep. So that's what we're going to be showing. So let's dive into our first scenario. So for the first scenario in Easy Racer, the idea is race 2 concurrent requests. So we're going to open an HTTP request, we're going to open a second HTTP request, and then one of those is going to get a response that says, hey, you're the winner, and then we should cancel the loser. And so this is the easiest, most kind of straightforward use of structured concurrency is a very basic race. And so we're starting with the simple thing. So let's start with the Scala ZIO code. So a few things to highlight about this. One, I'm using defer. And so the defer there is the ZIO direct syntax, which allows us to have a sequence of effects that are going to run in sequence. And we do that with the .run on those last two things. And gives us the ability to avoid doing a for comprehension or doing a flat map, that sort of thing. I really like the direct syntax for things like this. It just looks so clean. And Scala 3 is like significant indentation. I think this code looks really nice.
Yeah. I think we should talk about why your request is a value. And this is something that I think all new Scala developers sort of, or ZIO developers, let's say, effect developers, have to wrap their head around, which is, because we're deferring computation of this value, the request is not executing. So even though we're assigning to a value, it's simply a definition or a blueprint for what a request should look like.
So at this point, we haven't actually made a request yet.
That's correct. And then additionally, I think the interesting thing here is we see this .run annotation or method in this defer syntax. But let's be real here. This is still all just flat map. It's not actually running anything. But the beauty of the run syntax is that the winner on the left is actually the result type of what this HTTP server HTTP request returns.
So just an HTTP response.
Exactly.
Yeah, and so it makes it look like it's imperative and all happening here, but really it's getting unraveled into the flat maps underneath the covers.
Yeah.
And then reading the body is also an effect, and so that's why we have to do the body as string run. And so what comes out of this function is a ZIO. And so again, that ZIO is just a description of what's going to happen. And then we actually have to run that ZIO through the ZIO effect system to actually get our result. And so there's some other parts of the code that actually do the running. But I did want to actually run this one just so you can get an idea of how this actually works. So here's this open in IntelliJ. And if I run this one, I think it's set up to run scenario 1. So that should hopefully spin it up and run it. And IntelliJ is thinking about things. There we go. And then also I have the server running here. And we'll see that the server, all that it outputs for this scenario is the number of concurrent connections. So we get 1 concurrent connection, 2 concurrent connections, and then one of those responses comes back, and that response then says, hey, we now have a winner of the race. And in structured concurrency, as soon as we get a winner in a race, we should cancel all of the other racers. So we were talking about this looking like a racetrack, like with horses racing on it. And it would be kind of weird if, one horse crosses the finish line and all of a sudden they're like, all right, everybody get off the track. Like we, got to make room for other things. But in programming, we do want to make room for other things. We want to use those resources. And so that's why the cancellation is really important here.
Yeah. I think, if you're a bookie, like you want to have as many races going as possible. So, you want your scheduler to be a really good bookie. I think that's the lesson from today's talk. So
that's right. Your scheduler should be a good bookie. Okay. So that's the ZIO implementation for that very basic race. And just as we're beginning to explore Easy Racer and some of these implementations, I just want to pause and see, are there any questions about how that's working and the effect-orientedness and the race and all that kind of stuff? Or is that, maybe you all are familiar with ZIO and it all makes sense? Yeah, Ryan.
My question is more about the server. Is the server actually waiting for the socket to close to guarantee that it was actually canceled?
So not on this scenario, but we do get into a scenario where it does validate that. So yeah, so the reason with this scenario why we can't is that as soon as we return that response, then we've considered the race to be completed, and we don't have another mechanism to validate that they did actually cancel that second request that's the loser. But there is a future scenario that does do that validation. So each of the scenarios tries to highlight one particular piece of structured concurrency and the benefits of it. And this one is just like, do a very basic race. Okay, so that's the ZO code, nice and clean. Let's now look at the aux code. So the aux code being based on Loom, we can just do everything in what appears to be like this blocking approach. The one thing about this one that stands out is that rec is a def. So why is rec a def here?
So if you do anything with referential transparency, you'll very, very, very quickly realize that even though it may feel very nice to assign everything to constants, to vals, you know things are going to happen, and you know the result will be stored. The problem with this is, of course, if we assigned a val here, one request would occur, and then the race would complete immediately because the result would already have been returned. So we're basically deferring computation until we can pass it off into the aux implementation. And you said something here which was like that this is potentially non-blocking, and I have a little bit of a beef with this statement because this is a blocking race here. It's happening on Loom threads, so they should be fairly cheap. But the caller of scenario 1 will block until this race is completed. So even though maybe we're not blocking multiple true underlying OS threads, there is still blocking happening. It's just abstracted in such a way that we maybe shouldn't care.
Yeah. And we do see that with the method return type just being a string. And so we know that we are not going to get that string back until the race is actually completed. There is no other future. There's nothing there
right.
to
no
do
function coloring. I don't know if you guys have built anything with any sort of non-trivial effect or whatever. You end up with this virality where every function in your code base ends up with this return type. So here, one elegance of aux is that your return type is just a string. That's all you need.
Okay, so that's the aux one. Any questions about aux? Yeah.
So why does it say race of rec, rec? So why is it repeated?
We're racing 2 concurrent requests, so we do need to make one request and a second request. So that race takes vargs, I think we looked at it, and so we could specify as many as we want. But
because this is the def rec, so it's kind of
it's lazy, right? So the request has not executed. This is just a description of what a request should look like. So.
Yeah. Good question. Okay, moving on to Kio. So Kio, tell us about that signature for how scenario 1, what it returns.
Yes,
what
less than. Obviously, we all know what less than means. No, I'm just kidding. So this, here we can see one string thing on the left. We already know that's the response we're expecting. In Kio, we generally refer to this less than symbol as pending, or perhaps the Kio effect itself. On the right side, we can see fibers. So this is a string pending fibers. So just like in ZO, you effectively have an IO monad, which you're awaiting completion. In this case, we are awaiting futures being run, futures being resolved. Another thing that's really important to note that with algebraic effects, you basically split out all of your effect types into different things. And so I think the line, request.run may be a little bit misleading to you. Request.run does a transformation on the request effect type to enable it to become pending fibers. And so this is sort of something
that pending requests and turns it into pending fibers.
Yes, exactly. So I would say that this is not a strong point of Kio, and it's something that we'll take perhaps iteration or documentation or learning. But one of the beauties here, I think, is just how simple this is. Like I think this is very comparable to the aux example in number of lines of code and the simplicity of it. And I think that's pretty cool.
And rec is a val, so
yes.
I do like the it's effects, it's effect oriented, and so
deferred computation. Like if you really want performance, we secretly all know that deferring computation gives us a lot of benefits, but we won't tell that to Adam Worski. So
yeah. Okay, so the Kio version, nice and concise. Any questions on Kio before we move on to the next one? Okay. Okay, so then there's Java Loom. Oof. It's great that we can be on these non-blocking fiber thread pools. But what's in just raw JDK, I'm not using any libraries here, what we get is the ability to create a structured concurrency scope. And so I'm specifying the scope type to be shut down on success. So this is like a typical race where the first one that succeeds is going to be the winner. And then we use this like fork join way of working in the scope. So we're going to fork some tasks into the scope, and then on that scope.join is where it blocks and waits until there has been a winner of the race. But it's blocking on virtual threads, I would guess. So yeah, it should be lightweight. But
I think it's notable here, like a distinction from common effect types. You generally, fork and you get some sort of fiber response type or what have you. I think it's interesting that Loom sort of abstracts this away and just says, there's a scope. We're going to fork these things into this arbitrary scope, and we'll join whatever joins first, which I actually think is kind of elegant. But it's unfortunate that we are using Java because it's a little bit verbose. But I think we talked about this also. Like one of the benefits here is if you're integrating with Java apps, there's no need to download anything. There's no need to import libraries or add function coloring. This just works. And so that's a huge benefit to Java Loom is that it's out of the box. It's there for you.
Yeah. And taking efficient use of all the underlying threads
threads.
OS and all that. Okay, that's the Loom example. Questions on that one before we move on? Okay, so then Rust, Tokio. So I'm not like a huge expert on Rust. I need to go to John's thing and workshop and actually learn it someday. So there may be things wrong with the Rust code, and feel free to point those out. But this was our attempt. We did a little Rust hackathon a while back and worked together on these, and this is the best we could come up with, so it could be wrong. But there's a few things I want to point out here. One is that the function is an async function. So tell us, you've talked about function coloring. Give us the rundown on that.
Yeah, so if you've ever used JavaScript, if you've ever used many languages, right, they have this idea of an async function. And I think this is a little bit hilarious because in a way to avoid function coloring in your type signatures, they've essentially abstracted this into the language. And so in Rust, the Rust primitive is known as a future. It's very similar to other languages, but by suggestion of the language itself, Rust futures should be lazy. So this is a difference from Scala futures if you're used to those. I think one of the interesting things here is this async function request does not return a result type. It returns a future of a result type. And it so happens that this async is able to abstract or hide this for us.
And so you can see the awaits in there that are chaining, making the request, getting the body, and then that just propagates out to become an async function. Then
what's Tokio?
Oh, Tokio. Yeah, tell us about Tokio.
Yeah, so Tokio is an async runtime for Rust. It's what many people believe is the best async runtime. I think that's up for debate, but not today.
Like the best ever in the world?
No, I mean for Rust.
Okay,
for Rust. So
it did inspire ZO2's scheduler, right?
That's true. That's true. Yeah. So I think Tokio provides a macro here to do select, but I think that's kind of irrelevant to the point. In general, we're just chaining futures here. We're doing some race semantics and hopefully some interruption semantics, though. That depends on who you're asking.
Yeah. So it is interesting that Tokio select is the way that we do a race, and we use this kind of pattern matching syntax there in the select to perform the race. But it is a macro, and like you said, this is getting expanded out into some more complex code to do the race. So it's interesting that they use a macro instead of using a just library function to do this.
Right. Yeah. I think this is Rust macros, stream of input bytes, stream of output bytes. So I think it's who knows what's inside that, right?
Yeah. Someone knows. Okay, so that's the Rust Tokio version of scenario 1. Questions on that one before we go on to scenario 2? Clarifications. Did we say anything wrong about Rust?
Trivial, small clarification.
Yes,
You will
please.
see this in the Tokio docs. It's fairly common, but a lot of actual working Tokio users will skip the select macro because of the dynamic you just said and the fact that it's kind of its own weird DSL. It doesn't work with the formatter correctly, and so you can actually just call race or join or select with functions. This is handy because it's variadic. So you can have as many conditions as you want, and that's when people tend to reach for this. You can also do things that are similar to the Java example where you're just explicitly calling spawn and join, etc.
Yeah. And we'll get into an example of a spawn in a little bit. But thank you for that clarification. Okay, scenario 2. So with scenario 2, what we're going to do is very similar to 1, except for one of those connections that we make is going to just get closed by the server. And so this is trying to verify that when that connection gets closed by the server, what does that do to the race? Does the race fail? Does the race consider that a winner, with the winner being in an error? And so that was the point of scenario 2, is just to try to suss out like how does it handle failures? And fun thing on, we'll talk about it when we get to the Kio one. Okay, so let's start with the Scala Zio one. This is exactly the same as scenario 1 because the default semantics for race in Zio are that if that thing fails, if a racer fails, that is not considered a winner of the race and does not terminate the race as well. It's going to wait until it gets a winner that actually succeeded. So that's just default race in Zio. Ox, same exact thing as we had before, I'm pretty sure. So it's just the standard race. Also knows about those error semantics, and so cannot fail the race, or chooses not to fail the race if there is a failure. Kio, same thing as scenario 1 as well. One interesting thing is when I was working on building this one a couple weeks ago, I was like, hey, race is failing when I get this connection error. And the default behavior in most frameworks that I've worked with is to actually not consider a failure to be a race ending event. And so Flavio was like, let me fix that for you. And Adam was like, hey, I don't know, you helped me on some part of that, right?
Yeah, so I think this is a good point of libraries are willing to help you, and it's very important to just contribute back and say, this doesn't work how I expect it to. And this is an important part of structured concurrency. Things should work across libraries, and maybe you have to take some time to learn the differences, but I think in general, library authors want to build something that you'll use.
Yeah. So now the fibers.race in Kio works like many of the other races where it has to be a success in order for it to be considered a winner. So that's Kio. Loom, I think, is the exact same as before as well. So because we're using the shutdown on success scope. And then Tokio, also exact same. So great. So all of these frameworks basically have the same semantics for a winner needing to be something that actually successfully completes, and a connection getting closed is a failure. And so, yeah, all these look good. So you get into some of the other scenarios, we do see that there are some frameworks that do things differently. But for all 5 that we've chosen to show today, the semantics of a race are the same, with handling not saying failures are not going to terminate the race or be considered a winner. Okay, questions on scenario 2? We're going to zoom through some of these easy ones. Okay, scenario 3 is a fun one. Because this one says, all right, you have to be utilizing your resources efficiently to be able to do this run. In this one, we're going to open 10,000 concurrent requests to the server. And as soon as we open that 10,000th concurrent request, then one of those returns and says, hey, I'm the winner, and then you need to cancel all the rest. And so this one shows us, 1, are we efficiently using our resources? And then 2 is, what's the semantics for racing a lot of things? Not just 2 things. So far, we've only raced 2 things. What if we would need to race a lot of things?
And I think before we dive too deep, if we all just take a step back and say, how would I implement this using threads? And with, you have a nice large heap size, 2 megabytes, we're on the JVM, we're just gonna use OS threads because, we like to work old school. I think we'd very quickly realize, even if we could spawn 10,000 threads, joining these, interrupting these, this would be an extremely non-trivial effort. And this is why we have abstractions like effect systems, futures, whatever you want to use.
Yeah. So in Zio, what we're going to do is fill a sequence with our request effects. So not actually performing any of those effects yet, just the description of that effect. And then we use a Zio race all. Zio tries to make sure that you have at least one thing in your race, because a race is not really valid if it only has 0 things in it. And so the API for race all takes a single element, and then you can provide the sequence as the rest of the elements. And so there was another way that we could have done this was request.head.race, request.tail, and maybe there's even other APIs there. But did want to show the race all as one API we can use in Zio to do this race. But there we go. This one works great. I think I did have to turn off the Zio HTTP connection pool in order to actually get it to make the 10,000 concurrent requests and keep all of those open. But that was pretty straightforward. Yeah, anything else to add on the Zio one? Okay. Moving on to aux. So the aux one is interesting, and we were talking about the sequence fill here and how we have to provide the thing that goes into that sequence be a function. And so that's so that we can then lazily evaluate it with the race where we pass in the sequence later.
So if you exclude these, like this weird looking parenthesis and rocket looking thing, the unfortunate nature is that you would begin immediately in this thread blocking each request. So it would take, the full iteration of 10,000 requests, which of course, because of the way the server's set up, this probably would never complete. So I think this is a huge usability concern with aux. You're constantly having to pass around functions, which means you're getting into passing, lazily evaluation via deferring your application of parentheses or arguments. I think this is something we can all agree is a little bit difficult, but I won't try to push too much bias against aux.
But tell us about the signature for that race function. How it actually, it's overloaded, right?
Oh, yes. So race, the one thing that's pretty cool about aux is that it accepts, you can do var args, you can do a couple, or it also accepts a sequence of, so it's a race of type T, accepting a sequence of parentheses to T, which is a very arbitrary thing if you're looking at it. I mean, I think here it's pretty simple.
It does give you the deferred computation.
Exactly right, yeah.
Yep.
So.
But you could also pass a sequence that doesn't use the function if you did want to, I don't know.
I don't know why you do that, but you could do that.
But
yeah.
You could do that. Okay, so that's aux, works great. And then Kio. Very similar to the Zio one there where we've got our effect there in our sequence, and then we fibers.race that. So all pretty straightforward. Okay, now Java Loom, again, pretty similar to the one that we showed. We're just now in a loop adding our things into that scope, so doing the scope.fork with all those requests. Works great. Then in Rust, this is where things got a little bit trickier. And again, not being a Rust expert, this could be totally, completely wrong, but this is the way we figured out how to do it, was to use a multi-producer, single consumer channel so that we are essentially like spawning all these Tokio fibers, and then we're able to put things into the channel. And I think the way that this works, it's been a while since I wrote this code, but I think the way that it works is as soon as we get a response out, it goes into the channel, and then we do the rx.receive, which then gets fulfilled as soon as we get that one item back from the server. Can you explain that code better than I can?
No, I think there's one small semantic point which is very interesting, is that Tokio does this sort of tricky thing where it treats its own, let's say, execution framework, or we might call them fibers, but I personally don't have enough experience with Tokio to call them that. But it actually treats that as a future. So even though we're doing this async move, which is basically creating a future, right? The Tokio spawn, which is produced, is also a future. And if you invoke the pull method, it will look into the underlying async future, which is then can be pulled. So I think it's a very composable nature of Tokio, which I like, but it's also a very interesting semantics because it doesn't maintain the same laziness, which maybe I'm wrong about that, but it's where Rust features become ambiguous.
Yeah. So. One interesting thing on this one, and actually many of these different implementations of Easy Racer, is that I did have to set ulimit on my machine, the number of open files, to above 10,000 for this to work. In the JVM ones, I don't, and I don't know how all that works underneath the covers. But interestingly, that to open 10,000 concurrent connections in Rust, you have to up your open file limits. Where in the JVM you don't, for some reason. So, fascinating. Maybe somebody can explain to me why. Any comments on? Oh, our Rust guy expert just left, unfortunately.
We're done for.
Yeah, but does anybody have any issues with this code or want to explain things better than I have? Okay, moving on to scenario 4. So scenario 4, here's what where we get into the case where we actually want to test that cancellation happened. And so that is to the question earlier from Ryan, where we say, all right, we're going to do the 2 concurrent connections again, but one of them should have a 1-second timeout. And that 1-second timeout is going to allow us to verify that on cancellation, so on timeout, we then close the HTTP request that was open to the server, and then the one that's left open can then respond with the success that completes the race.
I think going back again to the sort of idea of like using threads directly, we can sort of think about how we might do this, but it may be non-trivial with thread interruption. So we probably throw a thread sleep in there, but how that interacts at the system level, it really is dependent on your scheduler and how all that works. But I think it's something to think about, like how would I do this if I was just using Java with OS level threads? So
would probably be hard. Okay, so in Zio, this is great. We can take our first request and add a timeout fail onto it that produces a timeout exception of 1 second, and then race that against our request without the timeout, and it just works. Super straightforward, easy, all non-blocking, all that kind of good stuff. Anything to?
Nope.
Okay. And then with aux, this one we get the timeout function that we can say, all right, add a 1-second timeout around this function, and then race those two. So pretty similar. The thread.sleep underneath the covers here.
Yes, so I actually dug into aux's implementation here. It seems like this timeout function is a little bit arbitrary, but it invokes effectively a race under the covers, and which is what we want to talk about.
Race a thread sleep with the...
Exactly. So it's using another Loom fiber or Loom thread to just do a thread sleep, which I think is pretty cool. It shows you that these simple thread abstractions can be used, especially when you have faster interruption on Loom.
Yeah.
So yeah.
So nice and straightforward there. Okay, and then with Kio, very similar to the Zio one there. We're going to do a fibers.timeout with our request and race those. Yeah, and I think it's worth saying again, timeout in most of these is implemented as a race.
Right, but another important aspect is that blocking an underlying OS thread is extremely expensive generally, especially if we have a limited resource pool. And so what most of these schedulers do is they have some sort of underlying abstraction, Zio.sleep. In the case of Kio, it's a fibers.sleep, or fibers.sleep, there's fibers.defer. All of these effect systems use an underlying lighter weight abstraction to sleep the scheduler to prevent this sort of issue of hogging whole OS threads for just a sleep.
Yep. Okay, then for Loom, in this one, we create a race within a race, which is really the same thing that the ones that we saw before in Scala are doing, but here we have to do it manually. There is no like timeout function. So we create a race that does the timeout and races that. Join until is basically just doing that thread.sleep there as one of the things that it's racing against. So now we've got this more explicit nested structure of a race within a race to do the timeout there. Anything to add on?
Just that your tree of execution is still a tree, even if it is just a line, let's say. So you have different nodes of scopes or whatever, but it doesn't really matter. It's still some sort of tree execution.
Yep. Okay, and then Rust Tokio. This one got a little more complicated, and again, maybe I'm doing some things wrong here, but I did want this request with timeout to be able to fail with both the timeout error and with a request error, because the request can fail. And so I created a sum type to represent that, and then had to do some kind of rearranging of the error types depending on if it was failed due to the timeout or failed due to a request error. But there is the Tokio timeout. I think that's from Tokio, that timeout function there. So I can do a timeout. And again, like the other ones, it allows me to easily do a efficient timeout and then essentially race that against the actual effect.
Cool.
Yeah, anything on that? Anything else?
No.
Okay. All right, scenario 5. So scenario 5, what we're going to do is raise 2 concurrent requests where a non-200 response is a loser. And so this is looking at, all right, sometimes we actually want to determine success or failure based on the thing that we're getting back from that effect. And so with this one, we have some different ways to determine what that success or failure looks like, how it gets determined. And on Zio, there's a filter or fail, which allows us just to look at the status in the HTTP response, see if it's a success, and if it's not, then it's an error. And then we can raise those. In aux, very similar. There's just a function to extract out that. We turn it into an either, I think it was, with that get right.
Yes.
And then that either then gets used to determine the success or failure. Right?
Yeah.
And then in Kio, in this one,
It's the default behavior.
The default behavior. So some HTTP client libraries will only consider a request to be a success if it was a 200 response. And so that's the default in Kio. So didn't have to do anything special there. Java Loom, we just have to go create a new class and make the request, check the body, throw exceptions. Like it's
If you're trying to increase the lines of code you write per year, this is an excellent strategy. I highly suggest this. Your manager will love you. So.
Yep. You can get promoted at Google for this. Okay. Rust Tokio, pretty straightforward there to call this special error for status function, which does exactly what we're looking for. If it's a 200 response, then it succeeds. If it's not, it fails.
I think it's notable how simple this is. I do think that direct style does offer some benefits, and the readability of saying, hey, this function does return, just after assignment, I'm just saying, hey, I want to make a change to what this looks like. I want to return it anyways, and it just works.
Yep. Okay, scenario 6. So what we're going to do is raise 3 concurrent requests where there's a non-tuner response is a loser. The reason why I added this one is because some of the frameworks I was working with had an arity of 2 on the race. And so as soon as I got to 3, then you're in a much more complicated scenario. We saw this already with the Rust one and having to not being able to use the Tokio select at a certain arity. But what about for 3? How does this change things? And so we've already seen this one with Zio, the race all, with aux. I think
var
it's
args. Yeah,
so,
it just works.
Yeah, it just works. And then with Kio, we can pass a sequence to race, so that's pretty straightforward. With Loom, right, we're just going to fork more times. And because it can be a non-tuner response, we left in that funny class rec. And then with Rust Tokio,
it does support 3, but of course, we always.
I don't know what the arity on that.
Right, I think the real test of abstractions is in production when you're using something. How far do I have to push to a limit before my abstraction becomes unusable? I have to reach into these escape hatches and pull them. And I think Tokio does a great job here. I'm sure it does a great job for many cases, but it's something to look out for.
Yeah. How are we doing on time?
We're at 10:43. So
okay, sweet. Okay, we're doing great. Okay, scenario 7. So this is a fun one where we want to do essentially what's called hedging. And hedging says, all right, I'm going to make a request to a server, and I'm not going to make that second request yet. I'm going to just wait a little bit. And if I'm in some threshold of time where, hey, that server probably should have responded by now, I don't know what's going on with it, but I'm going to wait some amount of time and then make a second request to the server. And that second request, so it comes later, and this is essentially hedging to say, something may have gone wrong with that first request. I'm going to give it a chance. If it doesn't work, then I'm going to try again. But then I'm going to race those 2 requests because I don't care. I don't really care if it's the first one or the second one that comes back, my hedge or the first request. I just want the first one, and then cancel the loser. So Google uses hedging a lot in their infrastructure. Many requests that come into Google's infrastructure get hedged. And the way that they set the hedging time is based on the kind of typical latency to a service. And so they're like, hey, if we're kind of outside the bounds of our typical latency, then we might as well send a hedge request because maybe we hit a GC pause, maybe something went wrong with the server, maybe out of memory, whatever. And so this can be a really great and easy way to improve essentially the P99 metrics so that your users are generally getting a good response. This, I think, can get really tricky when you're not in idempotent requests, right? And so it's not like the silver bullet that you can always just slap on everywhere. But let's look at hedging. So with hedging in Zio, what we're going to do is take one of our requests and put a 4-second delay on it so that after 4 seconds, that request will then be made. So pretty straightforward. Anything to add on
Yeah,
that?
I mean, the semantics here are effectively zio.sleep for 4 seconds, then just flat map that to the request effect. I think one thing to keep in mind with all of these tools is that if your scheduler is not performing adequately, you may not see accurate time in your hedging, and so this is something to watch out for. Actually, Cat's effect has a mechanism to detect if the ticks are not happening at the correct frequency. So it's something to watch out for if, watch how long your hedging takes. So
Yeah, interesting. Okay, in aux, because we're on virtual threads, we can just thread.sleep a request, and that's our way to do a delay. Pretty straightforward. And then Kio, similar to Zio, we can do a fibers.delay on an effect. Easy. Java, thread.sleep. And then with Rust Tokio, thread.sleep, basically. And so all pretty straightforward to do the hedge. Yeah, anything else to say on hedging? Okay, we got a couple more to get through.
You want to skip to 9 or you want to show 8?
Let's do real quick on 8.
Okay.
8 is we wanted to show opening and closing a resource and having that be part of the race. And so here's what it looks like in Zio, where we're going to be able to make a request. We want to check to make sure it's a 200 response. And then we have the open effect. We've got the use effect, where we're actually going to use the resource that we acquired on open, and then close. And Zio acquire release with gives us this really easy way to make sure that the open works, that we get the resource, we close it, even in the case of failure. And this particular scenario does fail on the use for one of the requests, so it does validate that hey, you actually did close that request even though you got a failure.
I think it's notable here that the close effect requires this or die semantics, which if you don't know, what happens under the covers there is we're saying, hey, trust us, really trust us, this won't fail. And I think acquire release with requires your finalization effect to be unfailable. And that's perhaps useful, perhaps not, but I think in general we want our closing or to be clean, atomic, whatever, so that's the hope there.
Yep. And there are other semantics in Zio for disconnecting the finalizer as well if we want to do that. But in this case, we didn't want it to be disconnected. Aux, pretty straightforward there with a delightful try finally. Yeah.
No, just keep going.
Just keep going. In Kio, there is a resources effect, which allows us to acquire a resource and provide the finalizer. So a little more code than the Zio version on this one, but I think pretty straightforward for how that all works.
Yeah, if you want to see this made better, you should make a contribution, figure it out, no.
Yep. Okay, Loom, just moving on.
I mean, I don't know if Tokio is much better, but
I think the Tokio one is at least pretty
it's clean,
readable.
right? It's simple, yeah.
Yeah, it reads well, but pretty straightforward.
I think the point there is that you need resource finalization, you need to be able to use resources effectively, and ensure that cancellation still works correctly.
Yep. Okay, scenario 9, this one I'm just going to skip over it. You can go look at the code. The point of this one is to show that a race is a very common thing to do with structured concurrency, but there are other things. Sometimes, so if we look at a race as being many to one, there are other things where we can just do many to many. Like let's run a bunch of things all at the same time and get all of their results back. So that was the point of scenario 9, was to show how we do that, and you can go look at that on your own. Scenario 10 is a pretty complicated one that tries to show cancellation of these like CPU bound tasks. And so it's really complicated. I'm not going to go into the code. Just want to point out one thing here, that Zio has this attempt blocking interrupt, which gives us the ability to actually go and cancel an effect that is CPU bound. And so
one notable thing there is that if you have an extremely low average latency and an extremely high tail latency, and so you think this is a good fit for you, you should know that attempt blocking interrupt introduces non-trivial overhead, as do many of these abstractions, right? When you want to do something which is more difficult, it costs more.
Yep.
So
you can go look at these on your own. I don't know. Was there anything else worth highlighting on?
I mean, just think about. I would question if you want to do this every day. And so I think Java Loom is awesome, but I think using Java Loom directly is probably questionable. So.
Okay, let's do some wrap up on kind of some of the high level things about schedulers. So first, we've seen this idea that we've got these different ways to schedule these tasks on virtual threads that in a lot of cases are abstracted. The Java Loom one, we're just working with it directly, but it's nice to have that abstraction. Why is it nice to have an abstraction over the scheduler?
I mean, for many things, but for one, like verbosity, lines of code, all of these amazing features. But for another thing, it generally prevents us from making mistakes, right? I think using effects, using futures, whatever you choose to do, if you follow idiomatic processes, it's much less likely that you're the cause of a leaked fork or some sort of unclosed resource where you didn't use Loom correctly. And so I think these abstractions provide sort of a veil or a cover over this icky direct thread utilization under the covers.
Yep. And then also, we can have the scheduler make some good decisions for us about how context switching should be managed, how blocking operations should be managed. Zio is just like updating the scheduler all the time, making it better, and I don't have to change any of my code. Isn't that nice?
Yeah. I think if you haven't been paying attention to the Zio 2.1 RCs, you should definitely go check out those pull requests. There's a lot of cool optimizations being made. And I think this is a great point that if you build code and it's fast enough on Zio as it is today, the hope is that library authors, Kio, whatever you use, can make this better over time. And I mean, this is sort of what we get into later, but this is a hope, and I think it happens a lot. But one of the problems with that is, of course, that you will get regressions. So if you're not monitoring your allocation rate, if you're not monitoring your CPU utilization, it's very important. I think in production, I've noticed these sorts of things, and it's very difficult to track down. So I think that's a con to this. But what are your other options, right? Like we want to choose the best abstraction, which gives us, operations as values, all sorts of other benefits as well.
Yeah. I had a fun thing where I tried to update the Scala Kio one to the latest version a couple days ago, 0.93, and something now is deadlocking because of something in the scheduler that changed. So, as Adam was saying, be careful with your upgrades. There can be many improvements made under the covers by having this abstraction over the scheduler, but there can also be new bugs introduced, so it can be a little tricky.
Yeah.
I think that was, we definitely don't have time to talk about composability and performance. That'll be version 2 of this talk.
Yeah, but if you're not using an effect system, you should be. If you're not using futures, you should be. Use an abstraction which fits your use case. But of course, I'm definitely a big proponent of effects and Scala specifically. So.
Yeah. Okay, we're out of time. We'll be around if you have questions. But thank you. Hopefully that was useful.